Hello and welcome to my video on why Hilbert spaces and operators in quantum mechanics. So the audience I'm imagining for this video is the following. I'm assuming you just took your first course, graduate course in quantum mechanics, and you did it well. But you left the course with a lot of questions that you got no answers there. Basically because you cannot cover all of that in a single course in quantum physics. But if you were like me, then you should have been quite mystified by what you have seen in that course. Of course, quantum physics is supposedly weird and strange and has a lot of new counterintuitive stuff like discrete energy levels and probabilities, and particles can be in many places and in no place at all, and things like that. So, but I'm not really talking about that here. In fact, while that is indeed quite different from classical physics, but you get used to it quite fast, I will say. But the great shock comes, at least in my experience, with a drastic change in the mathematical way we describe things and the mathematics we use. And in classical physics you get used to a certain language and then suddenly you change to a completely different one. And that's what I want to talk about in this video. Why are Hilbert spaces and operators used in quantum mechanics to begin with? So, let's get into it. In classical physics, you and for most of your undergraduate studies, you basically build your whole intuition on this framework: Euclidean three-dimensional space, or maybe even space-time, and a continuous trajectory of a particle or a mechanical system in it. And you use several tools from geometry, like calculus, differential calculus, to obtain quantities of physical interest, like, for example, the velocity, acceleration, and so on. So the mathematical framework we use for classical mechanics is differential geometry. We use differential geometry, of course, in the phase space formulation, the Hamiltonian formulation of classical mechanics, where a differential manifold is used to describe phase space and with a symplectic form. So it's basically classical differential geometry. So, but when you take your first exposure to quantum physics, you are presented with the following things. For example, things like the following: a state of system is a vector, not a trajectory anymore. These vectors can be you can make a sum of one vector with another. That's called the superposition principle, and basically you use a lot of tools from linear algebra. So we go from differential geometry in classical mechanics to linear algebra in quantum mechanics, operators and state vectors, and the linear structure of that space of state vectors. And actually, here a little clarification: it is not just linear algebra; it's actually a thing called functional analysis on infinite dimensional Hilbert space, which is a combination of linear algebra and topology, and that makes things quite a little bit subtler and delicate. And in fact, in infinite dimensional Hilbert space, a lot of things that you will think are valid because they are valid in finite dimensional Hilbert space are not really true in infinite dimensional Hilbert space. So one has to be really careful with that. So what happened with geometry? Suddenly we are with Hilbert spaces, operators, state vectors. What happened with differential geometry, with the trajectories and physical space and all of that? And that's, to me, the greatest shock when you are exposed to quantum mechanics for the first time. I mean, an actual systematic exposition, not a popularization. One when you actually see the gut of quantum mechanics. So what we will actually see in this video is that geometry didn't go away. It is actually there in quantum physics, only in a completely different way and in a generalized way. It is not classical geometry, differential geometry anyway. It is a different sort of geometry, but the main ideas of geometry are still there, and that's what is quite interesting about quantum physics. And the main geometrical idea that is still there will be the following, not in the classical way in which it will be presented now, but in a different way. But the same ideas will be still there, and that idea is the following. It is the ideas from measure theory. So what is classical measure theory? It is a generalized theory for dealing with integrals and probabilities, and you can see it as a generalization of what is the notion of a piece of space of a space having a volume. So the first thing we need to define is that of a sigma algebra. Now consider a set X and a collection of subsets, which will be called here in sigma X, and it is called a sigma algebra in X if the following properties are satisfied. And well, you can see the properties. X is in sigma X. If E is in sigma X, and then the complement is also in sigma X, and if you have a countable succession of elements, then the union is also in sigma X. A space with such a collection is called a measurable space. So we have now a set with a collection or with a special collection of subsets that satisfies this. So and this is useful for the following definition. which is that of a measure. A sigma additive, a positive measure in a measurable space will be a function defined on the collection of subsets from 0 to plus infinity. This is called the extended real line, where you include a point called the plus infinity, which satisfies the following. The empty set is 0, the function applied to the empty set is 0, and this is the function when you apply the function to the union of a succession of or a family of subsets from this collection, you get the sum of the function of the applied to the individual subset. So a measurable space with a measure is called a measure space, and this is useful for defining a probability space, which is a measure space in which the measure up when applied to the wall of the set, you get equal to 1. An abstract theory of classical probabilities is just an abstract theory, a measure space where the measure is a probability measure. And so I mentioned about geometry. Why I'm talking now about probabilities? Because measure theory is considered to be the most basic form of geometry. You can see you can think of a basic hierarchy of geometry as first and the most basic measure theory and measures, perhaps a probability measure there, then topological spaces, and then differential geometry. A differentiable manifold, you can see that it defines a special topology, and if you have a topological space, you can see that it defines a special family of measurable subsets, which is called the Borel sigma algebra. So if you have a topology, you automatically can have a measurable space, and you can define a probability measure there, which is usually called a Borel measure. So, and in physics, the basic space that takes the role of our X here is usually phase space. That's the set where you take, which is usually a differentiable manifold, and therefore it has a topology, and therefore it has is Borel measurable set. That's the measure space that is taken for defining a probability theory in classical mechanics. You use phase space as your measurable space, and you define your probability measure over phase space. That will be the basic geometrical structure of a probability theory in classical physics. Okay, so now we will consider how to go beyond the classical realm, because that's what will take us to quantum physics. So we need the notion of a lattice. A lattice is basically a set with two binary operations, which are usually called, this is the AND operation and this is the OR operation. and they satisfy the following properties. Not necessarily, we will not go into details of, but the properties are these. And an example of a lattice is, for example, classical propositional logic, where the AND operation is precisely the end of propositional logic, and the OR operation is, of course, the OR of propositional logic, and the set is, of course, the set of propositions. And you can easily convince yourself that these properties are satisfied in propositional logic. Now, another way of defining a lattice is the following. If you have a partially ordered set where the supremum and infimum always exist, you can define the OR and AND operations using dot, infimum, and supremum, and in that way you get a lattice on R. And on the other way, if you have a lattice, you can define a partial order such that you recover the previous way. So we will use this notion in an interchangeable way. Whenever it's convenient, we will think of a lattice as defined by the binary operation, or as defined by the partial order. Now, the following is a key properties that is not general, only some lattices have, which is called the distributivity property, which is the following. If you have the OR operation applied in this way, you can, of course, distribute. That's why it's called the distributive lattice. And the same way with the AND operation. For example, propositional logic is indeed distributive. Now, the following are very important properties of lattices, for example, which we will need in the future. A lattice is bounded if it has, from the partial order point of view, a maximal and a minimal element, which is denoted in this way. It is also complemented if it is bounded, and if you have what in propositional logic will be the negation operator or orthogonal complement, which satisfies the following properties. And sigma complete if for all countable families or successions you have a least upper bound in the or infinite or operator applied to the whole family. Thus, in this way, this thing converges to an element in R. That's why it's called complete, because it is complete. Now, the following proposition will be very important. All sigma algebra on a set, in the sense of our first definitions, is a Boolean algebra, and where a Boolean algebra is a distributive lattice that satisfies these properties, where the partial order is given by set inclusion. So we get the following identifications: or is the union of set, and is the intersection. The maximum and minimum correspond to the wall of the set and to the empty set, and ortho complements correspond to the complement set. So if we are dealing with sigma algebras on sets, we cannot go beyond Boolean sigma algebras, and that means distributive lattices. So in classical probability theories, we are always dealing with distributive lattices. So we defined the notion of a measure in a set. However, the previous proposition, we thought that if we see the sigma algebras of the set as lattice, they are of a very special kind. They are always a Boolean sigma algebra, which is always a distributed lattice. What will happen if we now try to see things from the lattice point of view, where we know we can have lattices that are not necessarily distributive? That is, for example, we got in sigma algebras defining a set, we got the identifications of the OR operator with the union. So, and if you recall, the definition of a measure used this union. So we can try to replace the union in the definition of measure by the OR operator and try to define a measure now on an arbitrary and abstract lattice. And in this way we could perhaps define a new notion and more general notion of abstract probability theories that are not necessarily classical, because the underlying lattice might not be a distributive one, so it might have new properties. So if we recall the points in the definition of a measure, we can see that our lattice will have to have at least some minimal properties. It will need to be bounded so that we have a minimum, so that the probability applied to that minimum is 0, and it will need to be sigma complete so that the measure when you apply it to the infinite OR operator gives us a convergent sum of the measure of the individual elements. So first we will see that there are indeed examples of lattices that are not distributive. And in fact, the example we will see, it will be the key example for our definition of a quantum theory of probabilities. But before that example, we need the following proposition, which will show us some properties to understand all of this in a better way. So consider a Hilbert space, a complex Hilbert space, and we'll consider as its set of orthogonal projectors. If you don't know what an orthogonal projector on a Hilbert space is, I suggest you to check on Wikipedia the definition, since we will not go into the details of the proofs of all these propositions and theorems. It is not you don't need to know everything. So first, the first property is that we can have a partial order in this in this set of orthogonal projectors, and that if two projectors commute with each other, they have special properties. This partial order is defined in terms of positive operator. We will not go into detail. The important thing is that you can define a partial order, and that partial order will allow you to define a lattice structure on the set of the orthogonal projectors, and that these special properties, when two projectors commute with each other, will give this lattice some special properties. So, and now the main example, which is the lattice of orthogonal projectors on a complex Hilbert space. So, this is a lattice under the previous partial order, which is bounded, where the maximum is the identity and the zero is the null element. Ortho complements are given by this sigma complete, and when the dimension of the Hilbert space is equal of or greater than 2, is non-distributive lattice. So it is definitely not a lattice coming from a sigma algebra on a classic on a set in the usual way as we defined it before. If two projectors commute, you have the following properties, and this is the most important. If you have a maximal subset of commutative projectors, then this maximal set, seen as a sub-lattice of the full lattice of orthogonal projectors, is actually a Boolean algebra, in the sense of being distributive and bounded, orthocomplemented, etc. But only if the projectors commute. So, we now define a quantum probability measure on that lattice, and we define it in the way we described it before. Since our lattice of orthogonal projectors is indeed bounded and sigma complete, we just replace the set theory element by the lattice element, and we get the definition of a quantum probability measure, which is a function defined on the lattice of orthogonal projectors, which to the interval, closed interval 0, 1, which acts on the following way. And in the OR operator, we get the sum, the converging sum. So we can see that we can indeed define a probability measure on a non-distributive lattice, and in fact in the non-distributive lattice of orthogonal projectors on a Hilbert space. So you can see that we are indeed starting to connect with the notion of probabilities that I promised in the introduction. But in this definition, we have what we could call a new mathematical degree of freedom, not present in the classical case, which is that now two projectors can either commute or not. So we call two projectors compatible when they commute, and incompatible when they do not commute. And this will bring very special properties to this probability theory. this is quantum probability theory. In fact, this will be the key distinction between classical and quantum probability theories. The existence, in the quantum case, of incompatible elements in the lattice. And now, as we mentioned, a sigma algebra on a set is a concrete example of a Boolean sigma algebra. Now, what about the opposite question? What if we have an abstract Boolean sigma algebra in the sense of being bounded, sigma complete, and distributive lattice? Can we find a set such that this abstract Boolean sigma algebra can be seen as the corresponding Boolean sigma algebra of measurable of a set? And well, we can indeed have the following results. The first is what's called Stone theorem, which tells us that all abstract Boolean algebras can indeed be represented as an algebra of subset of some set X. And not I say Boolean algebra and not Boolean sigma algebra. So it is not necessarily a sigma complete Boolean algebra. And in the case of abstract Boolean sigma algebras, we can indeed modify things so that we more or less can actually find some subset, so that we can indeed find an isomorphism between our initial abstract Boolean algebra and a set. So if we are in the theory of abstract Boolean algebras, we cannot go beyond Boolean algebras coming from sets. But what happens with the case of lattices, abstract lattices that are not Boolean algebras? Is there a representation theory? And in that case, in terms of what kind of mathematical elements or structure will this necessary non-distributed lattice will be represented? And so we'll need to impose a bit of first some basic requirements of being bounded or complemented sigma complete, but even that will not be sufficient to obtain our desired representation theory. So we'll need to investigate a little bit more the properties of the lattice of orthogonal projectors to obtain more properties and see if those properties are enough to obtain some decent representation theory. And the properties, the additional properties, are the following. Only 0 and 1 commute with every element of the lattice, and you can define the commutation in purely lattice theoretical terms. So we can translate this property into lattice terms. So we can impose that property on an abstract lattice, even if we are actually checking it in the example of the lattice of orthogonal projectors. This one is called separability, and this one is called atomicity. This is called the covariant property, and this one is called the orthomodularity, and this one will be the most important. You can see orthomodularity. I'm not going to explain it into details. as a weakening of distributivity. So we are indeed exploring abstract non-distributed lattice, but ones which are very close or perhaps weakly non-distributive, because we will impose this orthomodularity property. So, and we will now consider the representation theory of an abstract bounded orthocomplemented sigma-complete irreducible separable atomic lattice that satisfies the covering property and is orthomodular. Only when we impose all of those properties is that we can obtain some meaningful representation theorems for abstract lattices. But first we will need the following, which is a slight generalization of the notion of a Hilbert space. I will not go into the details, but it will basically amount to replacing the notion of an inner product space, vector space, in which you replace the notion of vector space over a field with that of a vector space over an involution ring, which is of course a more general thing than a field, which is a much more tighter mathematical structure. So you can think of this notion, a k-vector space, as a generalized Hilbert space, where this K is a ring, an involutive ring. And the involution you can see as generalizations of taking the complex conjugate. Of course, in the case of the complex field, it is indeed complex conjugation. Now, the first representation theory was obtained by Piron in the 70s, which is an abstract lattice with all the properties we mentioned before, is isomorphic to the lattice of closest subspaces of some k-vector space with the generalization of an inner product there. And recall that there is a one-to-one correspondence between closed subspaces and orthogonal projectors. So what basically this is telling us is that our abstract lattice is indeed isomorphic to the lattice of orthogonal projectors, but in a generalized Hilbert space. But note that we didn't include the orthomodularity property here. So what happens here to all of this? We indeed include the orthomodularity property, and in that way we get Soler's theorem, which was proved only in the 1990s, which is if we add the orthomodularity property, and if there is an infinite orthonormal sequence, then our generalized Hilbert space can only be a complex Hilbert space, a real Hilbert space, or a quaternionic Hilbert space, and infinite dimensional, of course, since we asked this property. So if we start with an abstract lattice with all the previous properties and orthomodularity, we get something very, very close to the mathematical structure of quantum mechanics, which is Hilbert spaces over the complex numbers. And if you add some other things like Poincaré symmetry, you can indeed see that the real case is contained in the complex case. So the real novelty here is that you can have quaternionic Hilbert spaces. And some of the mathematics of quaternionic Hilbert spaces are indeed being explored, but they have quite different properties. For example, if you know from standard quantum mechanics that you have a one parameter group of unitary operators, then you can define a corresponding generator, self-adjoining generator, and that's called Stone's theorem. And that theorem, for example, is not valid anymore on the quaternionic. And since we use that theorem, for example, for obtaining the Hamiltonian, then the physics of quaternionic Hilbert space is quite more complicated than the complex case of standard quantum physics. So the theorems in this section provide indeed a powerful justification for the mathematical formalism of quantum physics, which is probability theory on the lattice of orthogonal projectors on a complex Hilbert space. So the part about complex Hilbert spaces and probability measures, or at least complex Hilbert spaces, we can see that we can have indeed some justifications for that. And now we can see how, in the following we'll see how we can obtain, from our approach of probability theories on the lattice of orthogonal projectors, we can indeed obtain more of the usual formalism of quantum mechanics. And this is the key theorem, which is called Gleason's theorem. If you have a probability quantum measure, then there is always a positive trace class operator of trace 1, T, which is completely determined by the quantum measure, such that the probability of a projector is, you can calculate it by taking this trace. You can recall from basics in quantum theory that these T are called density matrices. So our approach via quantum probability measures on the lattice of orthogonal projectors, you can see that automatically gives us, there are no more quantum probability measures than the ones you can calculate by taking the trace with a density matrix. So this Gleason's theorem provides a powerful justifications for that rule, which is taken as an accepted axiom of or principle of basic quantum mechanics, that the probabilities are calculated using by taking the trace with a density matrix. And an immediate corollary of Gleason's theorem is the Cauchy-Specker theorem, which says that if the dimension is equals or greater than 3, then there is no quantum probability measure taking values only of 0 or 1. So you cannot have in quantum probability theory what in classical physics are called Dirac measures, which are measures that for all elements give either 0 or 1. And of course those measures are very close to classical physics, because if all probabilities are either 0 or 1, then everything is well defined in a precise way. Things either happen or not happen. The position is either 5 or it isn't 5. But what this is telling us is that in quantum probability this can't happen anymore. You will necessarily have intermediate values for the probability. So if you ask, is the position equal to 5, and then you will have only a probability for that, not a definitive answer in terms of 0 or 1. Yes, is 5, or no, it is definitely not 5. No, in quantum probability you can only have a probabilistic answer strictly contained in between 0 and 1.